Good afternoon, everyone. Thank you for joining this technical webinar. Today, we are very pleased at Diana FEA to have a guest lecturer, Dr. Dan Andrei Miklozoiu. He's working for Consolis, who is one of the European leaders for precast concrete solutions. And today he's going to present the work he did at University of Cluj-Napoca in Romania about the experimental and numerical analysis of different vertical connections of precast shear walls with special regards towards the deformability. So during this webinar, your microphone will remain muted, but you have the possibility to type your questions. There is a questions box. And from time to time, I will look at these questions. And at the end of the session, I will eventually raise the questions that are relevant for the large audience to Dan, or eventually we will get back to you by email later. As I mentioned, your microphone will remain muted during the whole session just to avoid background noise disturbance. And this session will be recorded, and after review from Dan and his company, we will publish eventually this recording on our YouTube channel within a few days. So keep an eye on our channel. So having said that, I think everybody is joining or about to join, and everybody can see and hear us, so that's all good. So I'm going to invite Dan to take over from now. So Dan, the floor is yours. You can basically start your presentation.
Thank you for the introduction. So my name is Dan Andrei Miklozoiu, and I'm here to present how I used Diana during my PhD studies. Okay, so let's start with an introduction. This study is regarding precast concrete multi-story structures, especially the structural design of precast structures that are using shear walls for achieving lateral stability. And it was assigned to me to assess how the shear wall behavior influences the design procedures. As we can see here, an example in FEM design. This is software widely used for global analysis of such structures. So we are to define the vertical connections and the horizontal connections, and we need to define their stiffness. And the response of the structure, and as it can be seen here, based on stress distribution in the base connection, we have a very high influence caused by the vertical connection stiffness. This is also shown here in these diagrams. So if the vertical connection stiffness is decreased, the shear demand in the vertical connection drastically decreases. However, if this stiffness is decreased, we will have higher demand in the horizontal connection. We will have more tensile forces, so we will need more reinforcement. So the goal of the thesis was set to assess the stiffness of different types of connections and to verify the design methods for some types of connections. That is to compare the design force values with experimental force values. And I will start with presenting the experimental study. We relied on the push-off test concept. This is a concept widely used for testing reinforced concrete and precast connections subjected to poor shear. We can see here the planning of the test setup in the laboratory. it is based on hinged boundary conditions, so the lateral displacements are not constrained for the specimen. So we had a new print pad and a spherical hinge and 2 hydraulic jacks that are loading the test specimen in the axis of the connection. And here is the test setup in the laboratory. For the measurements, we used a load cell to measure the shear force in the connection, and to attempt to measure the shear displacement, we used the displacement transducers. That's on one side of the specimen. On the other side, we used a digital image correlation system. That system allows us to capture fully the displacement field and to perform crack readings at every stage of the experiment. This is an overview of the experimental campaign. We had a lot of tests, but 9 of them were used for the ANAFEA simulations. You see here 3 test series. A test series means that one connection layout is tested 3 times. So we had 3 test specimens designed to be identical. These are the test specimens. We had 2 L-shaped wall panels that were cast in Romania into a precast factory, and we cast the joints in on-site conditions with materials that are used for such connections, with grouts and mortars, respectively. And the connection details imply using steel assemblies. So we have 2 test series that are using this steel assembly. We had 2 embedded parts casted into the concrete, and on site we had a third plate that is welded. For the third series, we had a threaded anchor that is embedded and a steel assembly, and the connection is achieved after bolting on site. And in the end, the connection is filled with mortar or grout. We have the shear key that allow a proper shear transfer, and for this series we had the shear keys equal to the wall thickness, and for the second and the third series we had reduced size of the shear keys. This is how we did the processing of the experimental measurements. We can see here the displacement field captured with the DIC, with the digital image correlation. And the first observations are that the rigid body displacements are very high compared to the very low shear slips. So the data requires some post-processing. Luckily, the software that we use allows us to automatically remove the rigid body motion, and we can observe here only the deformation components, and we can measure the slips with more control points along the joint height. So if we plot the values from 11 control points along the joint height, we can observe a very non-uniform displacement along the joint height. And for engineering purposes, we average these results, and in the end we express the stiffness of the connections with these equations. Here are the results from the experiments, the shear slip curves, and here we can observe the stiffness values calculated with these equations. And we can observe that we have a two-stage behavior for all the specimens. We have a very high initial stiffness that is close to the default rigid value considered in frame design. And we have a cracking moment. After that, we have a bilinear behavior. We have a stiffness reduction with a significant reduction of the stiffness. So this was a summary of the test results. Let's see now how I model this test in Diana. Only 2D models for these experiments. You can see them here for the 3 test series. The thickness of the elements was taken into account, was modeled by the finite element thickness. We had the wall panels and the support plates that are modeled with 200 millimeters plane stress finite elements. And we had the truss reinforcement modeled with truss elements. And the joint was modeled with plane stress elements. More trickier was to model the shear keys for the second and the third series. Here we had a reduced size of the shear keys, and the finite elements were at the thickness model to account this fact. Here are some more details about the model. Very important was to take into account an interface between the concrete and the mortar. I used the structural line interface with the nonlinear elastic friction function. And this function was defined with the parameters which were taken according to Eurocode 2, chapter 6.2.5 for very smooth interfaces. The interaction of the concrete with the insert was taken into account with in a simplified manner with the same approach, considering no cohesion and very little friction. Here is the assumption in modeling the steel inserts. These inserts have a very complex 3D geometry. The steel plates were taken into account by accounting their thickness into the finite elements. So we have 2 steel assemblies on each part of the wall, and one plate has 8 millimeters. So we had 60 millimeter plane stress element in there. The plates that are angled are rotated by 90 degrees and are accounted with this real thickness in the finite element model. For the reinforcement, I used beam elements that can account for the shear deformation. So class 3 beam elements. I defined a circular cross section that is equivalent to the fact that there are 2 reinforcements in the same section. And some reinforcements are bended, and they have a different strength if we look from a 2D perspective. Here are the assumptions for the interaction of the steel inserts. So we had welding, and the welding is quite complicated. So for our purposes, we weren't interested in a very detailed understanding of the local behavior. So in the model, I used the rigid connection options to model these weldings. There are some regions that do not interact with the environment, so these regions were disconnected. And as for the interaction of the reinforcement with the surrounding concrete, I used the bone slip model provided by Shima. This is most easier to be defined and was providing very good results for our purposes. Here are the material properties used in the model. So we were provided with test results, cubic compressive strength for concrete and mortar, and to use in the model the uniaxial strength based on cylinders. I used the ratio provided by Eurocode 2. For the tensile strength, we had tensile splitting test results and flexural test results, and again I used a conversion based on Eurocode 2. We had elasticity modulus test results, and for the corbels and the support plates, I used a simplification with linear elastic material properties. The material model used was the total strain-based crack model with a tensile curve assuming a brittle behavior. That is because this tensile curve was able to capture the brittle behavior that was observed during testing. As for the compressive behavior, the parabolic model with the parameters defined according to model code and according to RTD guideline. Very important for these models was to account the shear behavior, the shear transfer that occurs in cracks. I used the shear retention function based on aggregate size. We need to define the mean aggregate size, and it was assumed to be equal as the maximum aggregate size divided by 2. Here we can see the analysis models. I used force control analysis with arc length control plus line searches. I needed a large number of iterations per load step to remove the spikes in the curves. And due to the complex geometry of this connection, it was required to use a quite refined mesh. And when we had the results, we had to address the same issues that were addressed during experimental measurements. We had rigid body displacements that are caused by the corbels deformation. And this rigid body displacement have an impact on the global measurements, on the global displacements. So the rigid body rotation was calculated with a simple method that is described through the thesis, and all the analysis were post-processed with a Python code. And we can see here a comparison between the raw relative displacements extracted from these two control points and the post-processed curve. We had quite good agreement between the experimental results and the Diana results, the post-process curve. We can capture the initial stiff behavior, and we can capture the slip that occurs at the cracking moment. And we can see that the crack pattern is quite similar with the real one. These are observations using digital image correlation. We can see now the peak load. The failure mechanism is again in good agreement with the experimental observations. We can see the yielding of the anchor bars, and after the reaching of the peak load, the specimens during experiment behaved in a very brittle manner. We have an explosive failure followed by the two elements separation, and this behavior was not captured with a smeared cracking approach. We encountered the strain localization after the reaching of the peak load, and the same behavior can be observed for the second test series. We can see again a very good match of the shear slip curves, the numerical one and the experimental ones. And we can see very good reasonable agreement between the strain that occurred in the analysis and the measured strains in the experiments. We had strain gauges placed on the welded plates, and these are considered to be a reasonable match and inspire confidence into the models. Some issues occurred when simulating the bolted connection. We can see here that the experimental bearing capacity is half than the one predicted with the model. So I did some investigations. The influence was proven to be given by the structural interface that models the mortar to concrete interaction. The definition of this interface was taken based on Eurocode 2 factor, and we can see that model code provides a very different factor for this mortar to concrete adhesion, which is 10 times lower. And it seems that using this factor, we have a much better match between the experimental results and the model results. So I did some investigations. In the literature, I found experimental results for this mortar to concrete adhesion, and it can be observed that in the literature the test provides a very high spread of values. So I found experimental results that give for this factor values from 0 to 0.5. So this can be considered as a stochastic variable. And next, I continued with parametric analysis, starting with this cohesion factor for the interface. And we can see a significant influence in the models. This factor affects the stress distribution in the mortar and the concrete, and we can see a different crack pattern for different values. And it seems that this variable this behavior can be real we can observe different crack patterns in the experimental measurements, the experimental crack readings. After many parameter studies, I chosen to present the most interesting one. This is the parametric study of the joint height and the steel insert number. We can observe here the results. The joint height is scalable, and we can assess how the reinforcement ratio affects the behavior. And in the end, I collected all the results from the parametric studies, and alongside with results from the literature, I was able to do a comparison with the design equation provided by Eurocode 2. So we can see here that most of the results are between reasonable accuracy. So we have only few tests or model results that are on the unsafe side, and these were easily explainable. Alternatively, you can use the model code equation. This equation was proven to be much more on the safe side. And now let's discuss a little bit about the horizontal connections. The horizontal connections chosen for the study are implying a grouted splice sleeve. We had test results from the literature, tests that are subjecting such connections in axial loading and combined with bending. And you can see here the models that were prepared based on the description of the experiments found in the literature and on the assumptions discussed earlier in the presentation. So again, for the connection, I used the structural line interface with nonlinear elastic friction for very smooth interfaces, and continuity reinforcement, I used again the schema bond slip relation. We can see here the connection detail and the model assumption. And here are the results. Initially, there was a quite good match between the model results and the experimental results provided by the authors, but at higher axial loads, and we had the failure governed by concrete crushing, the model started to behave in a stiffer manner, and I was unable to capture the fully the plastic behavior. I forgot to mention these curves, the experimental ones, are cyclic envelopes, and the models were monotonic models with material properties that are used to model the monotonic behavior, not the cyclic behavior models. And these results are considered to be satisfactory since the study was regarding non-seismic regions. Then I move on in modeling a second benchmark experimental study. We can see here a column that is using again a horizontal connection with grouted splice sleeve, and we can observe the same experimental numerical comparison, the same behavior. The models are slightly stiffer and they are unable to capture fully the plastic behavior. And again, the plastic behavior was not the purpose of this research. And I moved into modeling a shear wall assembly. No test results for this kind of a test. So I used the connections that were tested in the past, that were presented previously. So the geometry of the shear wall assembly is confined to the geometry of the test specimens. And I used linear elastic foundation and two loading plates to apply incremental displacements. The reason for the application of the loading in 2 points is to avoid applying any pressure on the connection or applying any tension. You can see here a simplified approach. Now the vertical connection is modeled with the structural line interface with the user-defined values, and these values are chosen from the push-off tests that were presented earlier. The horizontal connections are modeled in the same manner as in the detailed model. And you can see here a comparison between the detailed model and the simplified model. So these models are run with different axial load levels, and we can observe that there is a very good match between the simplified model and the detailed model until we reach a certain lateral load level. At this load level, if we do the linear elastic analysis with fan design, we can observe that in the middle connection, we will reach the maximum shear load. And as seen in the previous slides, the detailed model cannot capture the post-peak behavior of the vertical connections. So if we look at the results, we can see that we have 830 lateral load, and at this load level we have the peak load in the middle connection. In the detailed model we have severe damage of the vertical connection, and in the simplified model we can see that we are almost reaching the peak load. However, we have 15% less shear force than estimated in linear elastic. The reason is the fact that we have a nonlinear stress distribution, and eventually we reach the maximum lateral load, a 22% higher lateral load. We reach the peak shear load. This shear load is calculated by summing the interface stresses, and we can conclude here that we have an okay safety margin for the linear elastic design approach. Now we can see a comparison with the design approach widely used for the horizontal connections. This is the sectional approach that is described in Eurocode 2. It can be applied for two independent shear wall with a free gap, or it can be applied for a monolithic section. And here we can see the interaction curves between the axial load and the bending resistance that were calculated with an application. And we can see here the results from the 2D Diana models. So at the lower axial loads, so at the lower lateral load levels, we have an equivalent monolithic behavior, and the behavior, the strength is reduced. We have impartial interaction between the two panels when the vertical connections starts to fail. Finally, we can see a comparison between the different failure modes that might occur for the vertical connection. We have an assumed perfect yield post-peak behavior in comparison with the brittle behavior. And we can observe the results here by doing a comparison in terms of lateral displacements for the shear wall. The results are set, the comparison is set between a monolithic wall and two independent walls. We can see here the lateral behavior for the perfect yielding behavior and the experimental observed behavior for the second test series, and for the situation where the brittle failure occurs and the maximum shear stress is reached, we have a rapid stress redistribution, and the shear walls are becoming independent quite quickly, and they reach the model with two independent walls, the lateral strength. So that was it. After the analysis, we would have some discussions. So Diana models were validated for the steel assemblies connections for the pre-peak behavior, and by using parametric and sensitivity studies, we were able to verify the design equation that is provided by Eurocode 2. With the correlation between the tests and Diana results, we proven monolithic equivalent behavior for these connections. And finally, we were able to verify the design strategy that uses linear elastic analysis for internal load determination and ultimate limit state design for the precast connections of the shear walls. And I would like to thank the involvement of both Consolis and the Technical University of Cluj-Napoca, and all the people that were involved in this study. And if you want to find out more about these studies and Diana models, you can verify the references. Thank you for the attention.
Thank you very much, Dan, for this very nice and comprehensive presentation. It was great to see how you could validate experimental results with numerical work, and also good to see how Diana was used in this topic. Good that you share the reference, because I see that a couple of people were asking if there was any publication or any available material to access. So the link basically that you provide, Dan, is the link of the publication. They are public. It's no problem to use that.
Yes. So,
okay.
Everybody can download the thesis, the experimental report, and the article that summarizes the first part of the thesis.
Okay, perfect. There are a few questions. Let me see. Because at the very beginning, you mentioned that you have been using Python scripting. Some people were curious to know what you were doing with Python. Was it to automatize your work? Did you do some parametric study? Could you elaborate a little bit more on that?
Yes, sure. Let's go back to that slide. So the Python scripting was used only for data processing. I outputted the nodal displacement results from Diana to comma separated variable file, and then I imported that file into Python and did the operation necessary to remove this rigid body rotation that was caused by the corbel deformation. So we can observe here that the raw relative displacement curve, it's very flexible, and it was quite unexpected outcome, since this is the linear elastic regime, so we should have quite good experimental match. And most of these shear slips are caused by rigid body motion of the extraction points that is caused by the deformation of the corbels. I hope
Okay, thank you for clarification.
More explanations are provided in the thesis.
Okay. Yeah, that's very good. I think some people will be interested to download the thesis and to have a look, because they are quite interested. There was another question. There was any plan to go for a full 3D model in this study?
No, a 3D model wasn't attempted. So, as I said, we were interested in we were not interested in a very detailed local behavior. So the 2D models were able to capture the stiffness of the connection and the overall behavior of the connection, the failure mechanisms, and the results were considered satisfactory. 3D analysis would be too much time consuming and will require more analysis time.
Oh yeah, definitely. I would say that when you can keep things 2D, I mean, you save time, and I would say that what you achieve shows that 2D analysis was definitely good enough. One last thing, because there were a few questions. Any issue modeling interfaces or controlling the interface behavior in this model?
Well, the issues occurred only for the third series. I can go back to that slide. We observed that the casting conditions for the third specimen was poor compared to the first two. And here we had quite low unexpected experimental result. And by considering a smaller adhesion or cohesion, as it's described in Diana factor or strength, I was able to capture the results. And I didn't mention in the presentation, but is discussed in the thesis. For the interface model, it is required to define interface stiffness, and I used the Diana 10.5 version. I didn't have the automatic definition of this interface stiffness, and I used the general relationship that is provided in the documentation as a guideline, and the models were defined with that values.
Okay, thank you for this clarification, Dan. I think I have covered most of the generic questions. So a lot of people are saying thanks for the presentation. So I would say at the name of the audience, I'd like to thank you one more time for the nice presentation and the very comprehensive way of presenting, Dan. It's very much appreciated. So I'd like to thank you, and also the university and the Consolis who are behind this work, supporting you. So as I mentioned, this webinar is recorded. Dan will review it, and maybe we need to do some editing. But after validation from Dan, within a couple of days, we will put it on our YouTube channel. So I'd like to thank you all for attending this technical webinar. Keep an eye on our website. There are more events and more technical webinars in the pipeline. And again, big thanks to you, Dan, for taking the time to present this very comprehensive study to us. Very much appreciated. Thank you all.